Welcome students. See, we have completed the material cutting topic and now we are going to solve the gate questions on that. So let us start with the gate 1 mark question. So as usual I am going to read the question, listen it carefully, and I will read the options also and then we will discuss. Question number 1. The cutting tools are provided with the large positive rake angles mainly for option A, increasing the strength of the cutting edge, option B, avoiding the rubbing action with the finished surface, option C, reducing the magnitude of the cutting force, and option D, better heat dissipation. So we know that when the rake angle goes on increasing, the cutting forces are decreasing. Of course, in positive side, when the rake angle goes on increasing, we are getting the sharp cutting edge, we are getting the point contact only. So yes, the forces are going to reduce when the rake angle is large, positive side large. Okay, so option C is correct, reducing the magnitude of cutting forces. Next question. If in the turning operation both the feed rate and the node radius are doubled, then the surface finish values will be, in turning operation both the feed rate and nose radius are doubled, the surface finish values will be option A, decrease by 50%, option B, increase by 300%, option C, increase by 100%, and option D, remain unaffected. Okay, so what they are saying, say F1 is the feed, F1 is the feed for first case and R1 is the nose radius for first case. They are saying on the second case this feed is doubled, that is 2 times F1, and this R2 nose radius also get doubled. Okay, so what is the effect on the surface finish? Surface finish पे क्या असर होगा? Okay, so we know that the relation between the nose radius and the feed rate for the surface finish, that is what? The surface finish RT is equal to F square divided by 8R, isn't it? So RT1, this is F1 R1 divided by RT2, if I write like this, so it will be F2 square by 8 R2 square, isn't it? So what is the surface finish? They are saying, say RT2 divided by RT1 will be what? This F2 is what? F2, this is 2F1 square divided by 8 times R2 is what? 2R1 square. Sorry, F square divided by 8R only. Okay, so into this original will be 8 times R1 divided by F1 square. So 8 get cancelled, R1 get cancelled. This is 4 F1 square. So F1 square is also get cancelled. Okay, divided by 2. So this is 2. So in the second case, this surface finish in the second case will be 2 times the surface finish in the first case. So surface finish is going to what? It is, what are the options? So of course surface finish यहाँ पे decrease हुआ, increase हुआ, double हुआ, that is decrease by 50%, no, increase by 300%, no, increase by 100%, double the rise, that is increase by 100%. That is the correct answer. Okay, next question. The size of built-up edge in metal cutting increases with, how the size of built-up edge increase? Options are with very high speed, large uncut chip thickness, use of cutting fluids, increasing positive rake angles. So we know that built-up edge are because of very high temperatures induced in the metal cutting tool. The small or microchips get added on the rake face of the tool. And why the temperature goes on increasing? Because of the forces are going on increasing in the metal cutting tool. That the result, the temperature also goes on increasing and built-up edge are formed. So of course the size of built-up edge increases when? So very high speed, वेरी हाई स्पीड पे क्या हो जाएगा, माइक्रोचिप्स भी निकल जाएंगे विथ हाई स्पीड विद द चिप्स, माइक्रोचिप्स आल्सो गेटिंग अवे फ्रॉम द मेटल कटिंग जोन. लार्ज अनकट चिप थिकनेस, yes, large uncut chip thickness, definitely larger force are required. यूज ऑफ कटिंग फ्लूइड्स, नो, कोई चांस ही नहीं बिल्ट अप एज बनने का. इंक्रीजिंग पॉजिटिव रेक एंगल, पॉजिटिव रेक एंगल जितना बढ़ेगा उतना फोर्सेस तो कम होगा, तो टेम्परेचर बढ़ेगा नहीं, तो बिल्ट अप एज आएगी नहीं. सो लार्ज अनकट चिप थिकनेस, दैट इज द करेक्ट आंसर टू गेट द increase in size of the built up edge. Next, crater wear always start at some distance from the tip because at that point we have discussed this in details, how this chip is getting lifted upwards by the tip of the tool, and after self weight or by the gravity it is falling down. Till that time the feed is given to the workpiece, so it will always strikes at some distance from the tip of the tool, where because of this higher friction the temperature rises more at that particular portion and we are getting this crater wear, isn't it? So the options are cutting fluid does not penetrate, option B chip tool interface temperature is maximum, normal stress on rake face is maximum, and option D tool strength is minimum. So of course this is because of the maximum temperature at the chip and tool interface. Next, the most of the metal cutting heat goes into chip, cutting tool, work material, machine tool. We know that maximum heat is carried away by the chip only. Around 75 to 80% heat is get carried away by the chip, which is whatever the heat generated. So उसमें से ज़्यादा heat कौन लेके जाता है, पहले chip, उसके बाद work और सबसे कम tool. We know the sequence. Next, cutting power consumption in the turning can be significantly reduced by. कटिंग पावर कैसे कम करने की पूछ रहे हैं, बराबर. सो व्हाट इज द ऑप्शन, व्हाट आर द ऑप्शंस? इंक्रीज द रेक एंगल ऑफ द टूल, इंक्रीजिंग कटिंग एंगल ऑफ द टूल, वाइडनिंग द नोज रेडियस ऑफ द टूल, इंक्रीजिंग द क्लियरेंस एंगल ऑफ द टूल. सो कटिंग पावर कंजम्पशन इज डेफिनेटली, पावर इज व्हाट, एफसी इंटू वीसी. सो जितना कटिंग फोर्स कम होगा अपने आप पावर क्या हो जाएगी, कम हो जाएगी. सो रेक एंगल बढ़ाओगे तो क्या होता है, फोर्सेस कम होते हैं, एंड फोर्सेस कम होंगे तो पावर अपने आप कम हो जाएगी. सो इंक्रीजिंग रेक एंगल ऑफ द टूल, दैट इज द करेक्ट ऑप्शन. नेक्स्ट क्वेश्चन, built up edge is formed while machining off. We have seen all these the mode of formations, or what are the conditions, which are the factors which can contribute for forming the built up edge, and with which chip. Discontinuous chip में तो built up edge आएगी नहीं, but continuous chip with built up edge and without built up edge, we know all the conditions. Okay, so options are built up edges are formed while machining off, ductile material at high speed, ductile material at low speed, brittle material at high speed, and brittle material at low speed. brittle तो गया क्योंकि brittle से हमको discontinuous chip मिलती है. so built up edge कौन से chip में मिलती है आपको पता है, that is ductile material with the low cutting speed, because there will be the time getting for the microchips to get added onto the rake face. okay, अगर ज़्यादा स्पीड होगा तो हाई स्पीड में चिप भी विथ हाई स्पीड मेटल कटिंग जोन से बाहर चली जाएगी, उसके साथ साथ ये छोटे माइक्रोचिप्स भी निकल जाएगी. सो द ओनली चांस इज द डक्टाइल मटेरियल विथ द लो कटिंग स्पीड इज करेक्ट आंसर. नेक्स्ट क्वेश्चन, द फ्रिक्शन एट द टूल चिप इंटरफेस कैन बी रिड्यूस्ड बाय. So how to reduce the friction at the tool chip interface? Options are decreasing the rake angle, increasing the depth of cut, decreasing the cutting speed, and increasing the cutting speed. Of course, increasing the cutting speed is only the thing we are having to decrease the friction between the chip and tool interface. जितना speed से चली जाएगी उतना friction क्या होगा, कम होगा. Next, the main cutting force acting on the tool during the orthogonal cutting operation of the metal is 400 Newton. Main cutting force दिया है, FC दिया है 400 Newton. The turning was performed using 2 mm depth of the cut. Depth of the cut 2 mm. Feed 0.1 mm per revolution. Then the specific cutting pressure. They are asking specific cutting pressure in Newton per millimeter square. So let us solve this. So I hope you are knowing the formulas. Formulas are very important. You can find many number of formulas in this topic metal cutting. Just collect these formulas at one place, okay, and try to memorize it, okay. So this is the orthogonal turning operation, dear. Then cutting force how much given? 400 Newton. Feed rate is how much? 0.1 mm per revolution. And depth of cut क्या दिया है? 2 mm. And they are asking the specific cutting pressure, that is UC, in terms of Newton per millimeter square. Okay, so we know the formula for UC is what? It is FC divided by BT1. VC cancel nahi diya. Okay, and in orthogonal turning we have seen that what is feed is nothing but our uncut chip thickness and depth of cut is nothing but our width of cut, isn't it? So FC is 400 divided by B is 2 and T1 is 0.1. So it is how much? It is 2000 Newton per mm square, isn't it? Let us check whether it is 2000 or not. Options are 1000, 2000, 3000 and 4000. This is 2000 Newton per mm square. Okay. Next question. If the Taylor tool life exponent n is 0.2, if the Taylor's tool life exponent is 0.2 and tool changing time is 1.5 minute, then the tool life in minute for the maximum production rate. I will repeat the question. If the Taylor's tool life exponent n is 0.2 and the tool changing time is 1.5 minute, then the tool life in minute for maximum production rate. So they are asking for maximum production rate. So if you remember, dear students, we have seen three criteria in the economics of machining: minimum cost criteria, maximum production criteria and maximum profit criteria. So out of that they are asking the tool life, okay, for maximum production rate. So in that case we know that this T is equal to what? This 1 minus n divided by n into TC, isn't it? So this is our what? The tool changing, TC is our tool changing time, n is the Taylor's exponent. So and they are asking for the tool life. Go and see the video, you get this formula there. So n is how much? 0.2 and tool changing time is how much? 1.5 minute. Put your value 1 minus 0.2 divided by 0.2 into 1.5. So you are getting around 6 minutes. So T will be what? 6 minutes. Tool life will be 6 minutes. So very easy. So you have to write the answer there. This is AME 2014 question. Okay, next question. A straight turning operation is carried out using a single point cutting tool on AISI 1020 steel rod. So simply you can say all steel rod. The feed is 0.2 mm per revolution and depth of cut 0.5 millimeter. The tool has a side cutting edge angle of 60 degree. Okay. So what they are asking, the uncut chip thickness in millimeter is how much? Again this is AME 2014 question. So here a straight turning operation is carried out by using a single point cutting tool on a steel rod. Feed is 0.2 mm per revolution and depth of cut. Feed is how much? 0.2 mm per revolution and depth of cut is how much? 0.5 mm. So here what is given? See, CS is given. CS is given, side cutting edge angle 60 degree. And then the uncut chip thickness they are asking. Okay. So please remember that whenever in the question if they are talking about the side cutting edge angle or the principal cutting edge angle, then there are a lot of chances that the given operation is what? The oblique cutting operation. And see, whenever if they want to ask the question for the orthogonal, you will find that orthogonal word every time in the question whenever the question is on orthogonal turning. So in this question no such a thing is mentioned about whether this is orthogonal, so nothing is mentioned. Please remember, there is always having the maximum chances that the question is from oblique cutting. And when it is 100% confirmed, when in the numerical they will provide the value of side cutting edge angle or the principal cutting edge angle, then of course the question is 110% from the oblique cutting. And see here, they are asking the uncut chip thickness, isn't it? Same thing they are asking, no? The uncut chip thickness, and you know how to convert this oblique cutting into orthogonal cutting. So if this is the oblique cutting operation, CS is given, you know that how to convert into orthogonal. You know T1 is equal to what? F cos CS in case of the turning operation, isn't it? So it is turning operation is given, so uncut chip thickness T1 will be what? F is 0.2 into cos of 60 degree. Or if they ask the width of the cut is equal to D divided by cos CS, D depth of cut 0.5 divided by cos CS, that is 60 degree. So let us calculate. So 0.2 cos 60, it is 0.1 millimeter. And if the width of cut, if they ask, it is 0.5 divided by cos 60, it is 1 millimeter. Like that you will get the conversion from oblique to orthogonal. And we require it whenever the oblique cutting is there, we have to first convert it into orthogonal and then we can go for solving the question. That is thing. And please remember, यहाँ पे अगर निकला है तो बता दूँ, whenever the question is on the economics of machining, please remember, whenever the question is on economics of the machining, whenever the question on the tool life, okay, or the surface finish, we are calculating by using the CS and by using the nose radius. So need not to worry about whether the question is on the orthogonal turning or oblique turning. Please remember, कहाँ पे even the effective rake angles, the question is there, then the question on tool life, economics of machining, no need to see whether the question is on oblique cutting or orthogonal cutting. Directly use the formulas, okay. But whenever, yes, such a kind of is given, side rake angle, side cutting edge is given, or principal cutting edge angle is given, or sometimes the tool signature is given. So tool signature generally जो CS की value last में, okay, the CS value will be at larger side in case of the orthogonal rake system, ORS system. But most popularly used is what? Which tool signature? ASA tool signature, okay. So many times only tool signature is given, then generally it is taking as the ASAs, because at more times or many places the ASA tool signature is only used. If not, they will provide you the into the bracket which kind of tool signature it is, whether it is ASA or ORS. Understood? Let us take the next question. In HSS, the tungsten can be substituted by, HSS means what? High speed steels. We have seen in the tool material that, see, in HSS there is T series HSS and M series. T series क्या होता है? जहाँ पे tungsten 18% होता है. M series में क्या होता है? वहाँ पे molybdenum आता है, isn't it? So tungsten is only replaced by what? Moly. So what are the options? Chromium, nickel, moly and cobalt. Of course the molybdenum is correct answer. Again, next question from the HSS, that is high speed steel tools. So in comparison to HSS, super HSS contains the highest percentage of. So super HSS are nothing but where the tungsten percentage are higher. So these are known as the super HSS. So sorry, not tungsten but vanadium. Vanadium percentage goes on increasing. We know vanadium up to 1% is there. 18% tungsten, 4% chromium and 1% vanadium. When the percentage of vanadium goes on increasing, it is known as the super HSS. So In comparison to HSS, super HSS contains higher percentage of course, vanadium, tungsten, cobalt, carbon, and vanadium. So vanadium is correct answer. And what is the basic function of vanadium? Increases the keenness of the cutting edge. Please remember. Next question. The amount of energy consumption for the unit volume of a metal removal is maximum A. Okay, so that is nothing but the specific cutting energy. Where it is maximum? It is maximum in the grinding operation. We have learned that, because in grinding operation the very small chips are there, very small material removal rate we are getting, and there are very high thrust forces, because the rake angle of the grit or grains, abrasive grains, are very large in negative side, up to 60, minus 60 to minus 80 degree we are having this negative rake angle. So rubbing action is more than the cutting action, that's why thrust is more. So that is the reason why the grinding operation become inefficient, because of large amount of specific cutting energy. Low MRR, high thrust forces, so specific cutting energy is more. So of course grinding is the correct answer. Options are turning, milling, reaming, and grinding. So high specific cutting is energy only in grinding operation. Next, in metal cutting with the carbide tool at the maximum recommended speed, the largest percent of heat generate goes to the, भले वो कार्बाइड हो या कोई भी टूल हो, मैक्सिमम जो हीट एनर्जी किस में चली जाती है रे? इन दी चिप, isn't it? So options are tool, chip, work, and tool post. So chip is the correct answer. Next question. The machinability of the steel is improved by the addition of sulfur, phosphorus, silicon, and all of the above. Yes, all of the above is correct answer. Next question. Only negative rake angles are used with the following tool materials: HSS, carbon tool steel, diamond, and carbides. We know that carbides are very weak in tension and very strong in compression. We can provide the negative rake angle, and we have provided the negative rake angle up to minus 10 degree on the carbide tools. Next question. Diamond cutting tools are not recommended for machining of the ferrous metals due to, डायमंड्स आर नॉट रिकमेंडेड. डायमंड का मेजर कॉन्स्टिट्यूटिव एलिमेंट क्या है? कार्बन है. अगर वो मैंने फेरस के साथ यूज किया तो क्या हो जाएगा? फेरस इज हैविंग ह्यूज एफिनिटी टू एब्सॉर्ब द कार्बन. सो कार्बन क्या आ जाएगा? टूल से बाहर आ जाएगा बाय द डिफ्यूजन प्रोसेस, इजंट इट? सो we have seen that diamond is not actually used for the cutting of ferrous materials. So see the options. Option A, high tool hardness. Option B, high thermal conductivity of the work material. Option C, poor tool roughness. And option D, chemical affinity of tool material with the iron. Yes, chemical affinity of the tool material with the iron is the basic reason. That's why we have not used the diamond as a tool material for the ferrous material. Instead of that, which tool material we have used? The cubic boron nitride, CBN, that we have seen. Next question. The angle of twist drill that determines its rake angle. The angle of twist drill that determines its rake angle is lip relief angle, chisel edge angle, helix angle, and the point angle. We know that how to calculate this. The angle which determines the rake angle. We know the formula, that is alpha b for this drilling, or on the drill, twist drill is equal to tan inverse of what? Half of tan alpha h divided by sine beta. So it is basically dependent upon the helix angle. Please remember, helix angle पे dependent होता है. So helix angle is correct answer. Next question. In orthogonal cutting process with the 0 degree rake angle, okay, the major cutting and thrust forces are 500 Newton and 250 Newton respectively. The coefficient of the friction between the tool chip interface. This is 2016 question. Okay, 2016. So we have seen the formulas. We have derived the formulas. So it is not like that I have only given the formulas directly in this chapter, metal cutting. So we have many times we have derived it. So this is based on the simple merchant circle diagram. We know that tan of what? Beta minus alpha is what? What we got from this merchant force circle diagram? This is Ft divided by Fc, isn't it? And when this alpha is equal to 0, what is tan of beta? Ft divided by Fc. That is, Ft is how much here? 250 and Fc is 500. So what is tan beta is nothing but what? Coefficient of friction, and same thing they are asking. So it is half, that is 0.5. So what is coefficient of friction? Is nothing but, you get the answer, 0.5 is the correct answer. Next question. Using Taylor's tool life equation, the exponent n is 0.5. If the cutting speed is reduced by 50%, the ratio of new tool original tool life is, okay. So new tool life to the original tool life will be, let us calculate. So we know the relation V1 T1 to the power n is equal to V2 T2 to the power n is equal to constant, okay. So here the cutting speed is reduced by 50%, that is, it is become V2 becomes half of the V1. So V1 T1 to the power n is equal to V2 is what? V1 by 2 T2 to the power n. So what they are asking, what is the new tool life to the original tool life? So T2 divided by T1 to the power n is equal to what? V1 you can get cancels, isn't it? So T2 by T1 will be what? Is equal to 2. And what is n? So T2 by T1 2 is equal to 2 to the power 1 upon n. 2 to the power 1 upon n is how much? 0.5. So it is how much? So this is 2 to the power 2 is nothing but 2 square, which is equal to 4. So new tool life will be 4 times the original tool life. Options are 4, 2, 1 and 0.5. So 4 is the correct answer.